Swift has been an exemplar mission, which has led to groundbreaking discoveries for more than 20 years in astrophysics. And the raise to a higher altitude, or a restoration of the original altitude of Swift, will allow it to operate for another 10 or 20 years. So given that we've had so many scientific discoveries and breakthroughs over the past 20 years, we have every expectation to keep that going, and for a fraction of the cost of what it would be if we were building a new mission. My name is John Nousek, and I am a professor of astronomy and astrophysics at Penn State, and I'm also the mission director of the Penn State Swift Mission Operations Center. Swift is a satellite designed to survey the entire sky for gamma ray bursts. Now it does many more things than that, but for the past 22 years we've been operating the Swift satellite from a mission operations center located here at Penn State. We initially were searching to discover the origin of a particular type of gamma ray burst called a short gamma ray burst, but we kind of solved that problem within the first 2 or 3 years that Swift was operating. Since then, we've moved on to a number of other targets. Recently there was a comet that came through from interstellar space that came through our own solar system, so this was an extremely nearby object, and we understood the material that came off the surface of that comet from Swift observations. So that was just one example, but virtually every year or two we've made groundbreaking discoveries with Swift for more than 20 years now. The new mission is called Swiftly. And Swiftly is a combination of 2 different satellite missions. It's a combination of Swift, and it's a combination of a satellite called Link, which has got the capability of doing the rendezvous and the boost. So the combination of those 2 is called Swiftly, and we're very definitely a part of the Swiftly mission. We've been practicing doing what we'll need to do when we're in a close connection, and eventually hopefully link up to the Link satellite. As I said, it's every bit as good as when it was launched. In fact, in some ways it's better, because we have improved calibrations, and some of these repairs that I talked about actually made the systems work better than they did originally. So when we stopped operating, in fact for last year that we have the full set of numbers for, we actually had more than 1,400 targets proposed to us by astronomers around the world to use Swift to observe. And that produced hundreds and hundreds of outstanding scientific papers. And we would like to restore that level of function. It's not one area, it is many, many areas of astrophysics, ranging from inside our solar system to actually at the very edges at the beginning of time, going back to when the universe was less than 1 billion years old. The way that Swift is particularly unique is how rapidly it can respond. The name Swift was chosen. Its namesake is the bird. There is a bird called a swift. And the characteristic of a swift is it's very fast to fly and very agile and very quick to catch its prey. So we use that inspiration for how Swift does its science. We on occasion can receive a request to observe a target and then be looking at it within a few minutes. That's extraordinary. There's not any NASA satellite that has that kind of capability. The typical satellite takes at least a day or 2, and more typically months or even years, before it can make an observation. So it hurts you if you need to look at something in what we call monitoring, which is to look at it repeatedly. With monitoring, you can tell whether you're just looking at one unusual circumstance, or whether this is the normal pattern, or if there's some variability that can be explained by some kind of a theoretical model or stuff like, or things like that. And so that whole capability is very well handled by Swift. If you're a scientist or even just a person with a curiosity about the universe, you get inspired by seeing what's in the universe, and whether it's a beautiful picture, whether it's some theory, whether it's something that may even have some practical use. All those things are true. But if you put that aside, the other thing is that We especially now are launching many, many satellites, a huge number of satellites. SpaceX is an example of a company that is plans to launch thousands of satellites. Those mostly are intended to be just thrown away or let fall out on their own. So potentially there is the possibility of saving billions of dollars by being able to reclaim and reuse these satellites. Or there's also the possibility that if a satellite would be determined to pose a risk to human life, the ability to fly up there and change how it would, where it would fall out of the sky would be a very useful capability. And we do have to keep the satellite supplied with where it's supposed to point.
In the same software that we developed, over 20 years ago.
And the people that build Chandra, they have to do the most trivial things have to be calculated from the ground and then sent up.